Okay, the third talk of this session is on fully dynamic graph sparsifiers by Ty Abraham, David Durfee, Yanis Kutis, Sebastian Kriniger, and Richard Peng, and David is going to give the talk.
All right, thank you for the introduction. So first, we should probably define what we mean by a dynamic graph. It's going to be very simple for us. We're just going to consider a graph. Yes. Speak up, or is the mic not working? Okay, gotcha. So we're just going to consider a dynamic graph where we just take a graph, we add edges, delete edges. For the purposes of this talk, assume that the graph is unweighted, but we do extend our primary results to weighted graphs. So our primary three results are we're going to have a dynamic cut sparsifier, a dynamic spectral sparsifier, and we're going to have a vertex sparsification routine, which we can also extend dynamically. So just to give a sense of what this means, we have our original graph, we have a sparsifier. We want that for each insertion and deletion of an edge, we maintain the data structure of our sparsifier. So anytime somebody asks us what does the sparsifier look like after any edge insertion or deletion, we should have a data structure that represents the sparsifier, and we can tell them exactly what that is. So these three results, as I have on the side here, we get a polylog worst case update time for the cut sparsifier, a polylog amortized update time for the spectral, and a worst case polylog for the vertex sparsifier. So you might be thinking, why would we want to update this every single edge? You know, why not just wait for all these edge insertions, deletions to take place, and then sparsify our graph? So we're going to first give one motivating problem that we have in our paper that sort of gives a reason why we want to do this for every single edge insertion and deletion. So that motivating problem, we believe, is actually quite closely related to some of the last work, which was dynamically maintaining a max matching. So this problem has received a lot of recent work, and our problem will be a bipartite undirected graph, and we're going to dynamically maintain the minimum cut value in polylog time. So the reason we believe that this is closely related is because it comes down to a very similar key subproblem. We want to consider graphs in which there's a small vertex cover, and we want to be able to quickly compute minimum cuts on these smaller graphs. And so again, remember that the whole reason for giving this motivating problem is I'm going to show that our dynamic cut sparsification, our first tool, is going to be integral in solving this problem. And we believe that this is a reasonably important problem, and as far as we know, we are the only people that have gotten as good of an approximation on this problem. So what do I mean a bit more by this key subproblem? Right, I want to be able to reduce to a small vertex cover size graph and compute min cut on that. So suppose this is basically a representation of our original graph, but the vertex cover is kind of small. It should be kind of small in this graph. The X is going to be our independent set. We have these vertices coming down onto the vertex cover. The idea of what we want to do with this problem is we want to get rid of a lot of these independent vertices, and so that now we have a graph that's proportional to our vertex cover. Now suppose we solved a minimum cut on here. Right, a minimum cut is a partition of the vertex set. So we've reduced our vertex set significantly, so what does that mean for the original problem? It's going to be incredibly simple. We're going to take the same partition of vertices on that subset, and then we just minimally extend it. So what that means, right, if we consider the vertex on the left side there, it has two edges going to one side, one edge going to the other side. We'll cut the one edge instead of the two edges. And this is for every single vertex we do this. And because each is independent, we can obviously do that property. So just eliminating vertices, right, that doesn't make a ton of sense. You're just getting rid of a ton of things, and the minimal extension could then be huge. You have no idea what the minimal extension is on the right side if all we did was just eliminated vertices. So we want to give some sort of representation of what these vertices should give in the original cut, but do it on this much smaller graph. So our tool here that we're going to use is the Schur complement. This is a previously known tool where you take a vertex, you look at its neighbor set, and you're going to project down to a clique on that neighbor set. So recall that this neighbor set is going to be in the vertex cover. Right? X is our independent vertex. This neighbor set is in the vertex cover. We're projecting down onto a clique in this vertex cover. So all these weights should then represent well what the minimal extension of X is, but it's representing it within the vertex cover. So a bit more clearly, what do I mean by this? Suppose in the vertex cover we separated A and B from C and D. This was our minimum cut that we decided upon. The minimal extension of this, once we brought it back to the original graph, should be weight 2. We could cut either side, they're equal. If we cut in the cleek, it's going to be weight 1, the cut. So basically this cleek, this added edges, and it added a weight 1 edge to this specific cut. And we claim, of course, that that is a 2 approximation of the weight. And similarly, suppose if we cut 3 on one side and 1 on the other. The minimal extension here would be to cut just the 1, and the cut of D from the rest in the cleek would give 3/4. And this would keep the 2 approximation. So this sure complement tool, right, projects a cleek that gives a very good representation of what the minimal extension weight will be for any cut that we take within this smaller graph. And the sure complement can be extended to any degree and non-unit weight. So in the static sense, this quickly leads to an algorithm where you would just take every single independent vertex, you would sure complement it down. So the independent vertices are the ones outside of the vertex cover here. We're projecting them down onto a cleek of their neighbors. Right? We would just solve in this much smaller graph, and then we would minimally extend the cut. And this would be a 2 approximation both on the minimal cut and on the minimal cut value from the previous slide. So obviously we wanted to do this dynamically. So where does this go wrong? Right? Suppose our vertex cover is sized like root n, and one of the independent vertices connects to everything in the vertex cover. Right? We delete one edge from that, we have to update that entire cleek of neighbors. With the sure complement, right, we would have to, I hit a little bit of the details, but you have to update weights of every single edge. So we're talking about n edges here that we're having to update. Obviously bad in this case. So we want to avoid having to sure complement large degree edges. And so this is exactly where our cut sparsification, our dynamic tool, comes in that we're going to first dynamically cut sparsify the graph. And what this is going to give us is a whole lot of these independent vertices are going to have low degree as a result. And this is going to come directly from the low arboricity property. And by low here, we're going to mean polylog. A polylog low arboricity property that is a direct result from our dynamic cut sparsification and is why we think that this tool can be very critical for many dynamic problems. Sort of a natural segue then into our first tool, dynamic cut sparsification. So just a reminder, we claim that our result is that we got this in polylog worst case update time. So for those who haven't seen cut sparsification, quick review. Suppose we have an original graph with m edges. We want to take the same vertex set and reduce the number of edges to n polylog. And for any cut in the original graph, that cut in this new graph should be within an epsilon approximation of the weight. And this should hold for every single cut. So naively, how might we do this? Suppose we wanted to reduce half the number of edges in our graph. Let's take the original graph. We assumed it was unweighted. Let's flip a coin on every edge. We remove it with probability of half. We give it weight 2 with a half. So each edge should remain the same weight in expectation. And so if we took any cut, the weight of that cut should in expectation be the same. And if we have a cut that's large, there's at least log n edges, this weight is going to be concentrated around the expectation. So it's going to be within an epsilon approximation with high probability. So where can this go wrong? Small cuts, essentially, right? We just showed that big cuts are fine. Suppose we just have one edge crossing 2 components. The weight of that cut is going to be 1. We flip a coin on that edge, it's going to be 2 or 0. And obviously, this is not a good approximation of what the value of that cut should be. So solving that problem. Suppose instead we took our original graph, we take a tree, we remove all the edges of the tree, we find another tree of the remaining graph, we remove all those edges, and we repeat this log n times. Then we're going to sample the remaining edges. So it's the same routine, but we're going to keep log n different trees that are disjoint in the graph. And so how is this okay? Well, suppose we have a cut with less than at most log n edges. Right? We look at the first tree, we remove all the edges. We should have removed at least one edge from this cut. This was a spanning tree, so if there was an edge crossing it, it should have been removed. There should have been at least one of them in this tree. We do this again for the second tree. We should have reduced the number of edges by at least 1. We repeat this log n times, we've completely eliminated all the edges from the cut. So what does this imply? No edges in a small cut are sampled. So we don't have to worry about variance being bad. We're not sampling anything. Every cut that's small, we're just keeping all the edges with probability 1. So this gives the full static routine for reducing basically the number of edges in half. So how would you reduce it to n poly log n edges? You would just repeat this process log n times. So the inner part of that, the algorithm is exactly the same as what I just showed. We're just iterating it log n times. So basically the idea is we just find log n different disjoint trees, we flip coins, we find log n different disjoint trees, we add that to the previous one, we flip coins, again and again log n times. So this just gives us log squared n trees, polylog trees. And this is exactly the low arboricity condition that we desired, that was necessary for our algorithm that we just showed previously. So this low arboricity property has also been recently shown in other dynamic algorithms to be very useful. So this gives further reason that we think it could be applied to other dynamic problems. So a main part of this paper, right, this was the static routine. This was known. This was not our results. Main part of this paper is that we're going to combine static routines that are known, sparsification, with some dynamic data structures that are also known. And with some work, we're going to give our dynamic cut sparsifier. So this was the static routine. The dynamic one that was previously known is that if you have a spanning forest, you can dynamically maintain it in worst case polylog time. So is this tool quite enough? Not yet, because right, we have these log n different trees, and they're not independent of each other. They do depend on one another for how we find these trees. So what do I mean by that, right? This was our sort of our peeling process, right? We had our original graph, we took a tree, we removed that tree, we found another tree, and so on and so forth. So suppose we delete an edge in the graph, and that edge happens to be in our first tree, right? At most, one edge should then be added to this tree from the graph to connect the components that may have been disconnected. But then, of course, we need to delete that edge from the subsequent graph. So this edge could then be in the next tree. We add at most one edge. And this process could repeat all the way down. So the reason we're fine here is because we're adding at most one edge. Right? That should be reasonably clear. And so at log n depth, we can do polylog work at each depth and still have a polylog worst case update time. And so this would be the basic idea. And with a bit more work, we'll give the entire dynamic cut sparsification routine. So let's move on now to spectral sparsification. This one, recall the claim was that we could get amortized polylog time. And it's going to be very closely related to dynamic cut. I won't have time to go over exactly what it means, but the Laplacians are close for spectral sparsification. The algorithm is exactly the same, except for one part in bold, in which we find a spanner instead of a forest or a tree. So the definition of a spanner, a log n spanner we'll use here, is that for any edge in the graph, we should be able to find a short path in the spanner between the two vertices of that edge. So if you think about trees, right, those are all n-1 spanners. For any edge in the graph, if we have a spanning tree, we should be able to find a path between those two vertices, and it has length at most n-1. This, we have a slightly stronger condition in that the path has to be short, and this may not actually give us a tree. Requiring a spanner may be a bit more edges than a tree, and we may have cycles within our spanner. So this is the static routine. This is known, and we also have a tool in the dynamic that is previously known that we can maintain an amortized polylog time. So you may think that this is just then going to give us the result in exactly the same way as the cut did, but it won't exactly. So we have the same routine. We're worried about deletions, compounding. So T1 is now our spanner. So we delete an edge in the graph. We deleted this edge from the spanner. Now notice that spanners, right, they preserve some shortest paths. So it's not just we need to connect the components back. We may have deleted an edge that was critical for many shortest paths. That many paths between vertices use this edge in a very nice way such that all of them could get their shortest path. And so it's possible that we could use log n edges to patch up each of these paths and give a path between each of these vertices. Right, so now we would need to use all of these edges in the spanner of T1, and this would require the deletion of all of these edges in the subsequent graph. So now assume this process repeats, that each one of these edges that we deleted in the spanner in T2 was critical for shortest path, added log n edges to patch up each of these shortest paths, and so now we had to use log squared n. This process repeats, and we're deleting log to the log. So it's not going to be an immediate extension that we can just use this tool with the static routine. Additionally, let's look at additions, right? Suppose we add an edge to G. This edge could be very nice for us for a lot of shortest paths, right? The spanners, we want to keep them reasonably small. Our whole goal is to sparsify a graph. We want to remove edges. So this edge can now be very useful for finding a lot of shortest paths that we had to do sort of long way with a whole lot of edges before. So adding this one edge to T1 could result in us actually removing a lot of edges from this spanner that are no longer necessary for shortest paths. So it could be log n edges that we're now removing from this spanner, which of course implies that we're going to add those edges to the G minus the spanner. So now those edges could all be very useful for the subsequent spanner. Each one needs log n edges that now are unnecessary. It removes them. We have log squared edges that we're removing. This process compounds, and we're adding log to the log. So these are essentially the two issues now that we need to deal with for getting our amortized time. So we solved them by slightly modifying our dynamic sparsification routine. What we're going to add is a monotonicity property. And so the claim is going to be that if we consider the previous slide, we're going to keep in some of these somewhat unnecessary edges. If we add an edge to the graph, and it's very useful in the spanner to be a lot of, it was for this slide, right? We added this edge. It was very useful for a lot of shortest paths, so we saw that we could remove a lot of edges. We're not going to remove those edges anymore. We're going to leave those edges in the graph, and we only remove an edge from the spanner if it's deleted in the original graph. So this should immediately imply, right, that we have removed the additions compounding problem, right? And the issue could then arise that, right, we're leaving in edges that might be unnecessary now, right? So we did want to bound the size of the spanner. We wanted these spanners to be polylog size. So we then also show within our result that the expected size will still stay that small. The spanners will still be n polylog size, n log cubed to be more specific, even though we're keeping in some edges that may be unnecessary. So then in addition, we need to now deal with the deletions, right? And so the deletions have a slightly nicer property in that they can only move up a graph once. Each edge can only move up a spanner one time, right? If they started at the bottom, if we delete it, it can only move up once. So this log to the log is actually really bounded by n polylog, right? We can't remove more edges than were in the original spanner. And so with this, we just sort of say after m deletions, this deletion compounding in total could only be n polylog size. Each edge can only move up one time. That the number of times is bounded by log, and the way they work their way up can only be bounded by n polylog for many edge deletions. We combine this, so I glossed over a little bit what the sequence of edge insertions deletions meant. It's in fact that we have this sequence be fixed, and what that means is that we don't get to see it necessarily, but that because our construction of these was somewhat randomized, an adversary could not constantly pick an edge that compounds deletions. So we show that it's very unlikely that such an edge that compounds deletions will actually be chosen. So combining these two arguments will then prevent the edge deletions from compounding too much, and we can bound it by an amortized amount. So I won't have much time to go over vertex sparsification, and especially the dynamic part, but the tool here we're going to have is we're going to be able to minimally extend cuts in a 1 plus epsilon approximation. So just a quick review. Hopefully you guys remember a little bit. We had this 2 plus epsilon routine. We sure complemented each vertex down onto this smaller vertex cover. we solved it on the smaller one, and we extended it. And remember that we sparsified the graph first, and we did this on low degree edges. So we wanted to see, can we improve this to 1 plus epsilon? And we were, in fact, able to. And instead of using the Schur complement routine, we sampled edges. And the way we sampled them is actually very, very closely related to cut sparsification, and that we thought of, well, what would be an important independent vertex? Well, suppose you cut the vertex cover, and it was the only one that gave a minimal extension to this cut. It was the only one where you had to figure out what edges to cut. Every single other vertex just projected down onto one side or onto the other side. This could then be considered an important cut. Right? It's the only one where you have to consider the minimal extension, so it should be included. So basically, we just want to make sure that if we're sampling one, there should be a lot of edges that are also being kept within that cut. There should be a lot of minimal extensions that we're keeping. And so we just find these by spanning trees in the Schur complement. Further problems, sorry, I have to rush a little bit. Further problems, we want to see if we can improve the dynamic sparsification to a worst case polylog time, and if we can apply some of these tools to other problems, such as max matching, sparsus cut, or balance separator. Sorry? Oh, yeah. So the epsilon, I just ignored them, but yes, the epsilon is within that. And over epsilon. I don't believe so. Talk about it offline, but I don't think so. Well, certainly not that we know of.